What could a tiny computer chip possibly have in common with a massive hunt for dark matter? Well, the answer is a single fundamental rule of physics, a rule that shows us exactly what happens when the simple models we learn break down and a much, much stranger reality takes over.
So, what's the connection? What's this invisible thread tying a supercomputer to a deep cosmic mystery? The answer is surprisingly simple, and it all starts with a convenient lie that most of us are taught in school.
Okay, so this lie I'm talking about, it's probably the very first thing you ever learned about electronics. And look, it's an incredibly useful shortcut, but at the end of the day, it's still just an approximation of the truth.
Remember back in science class, you're taught that when you flip a switch, the light comes on instantly. The current just appears everywhere in the circuit at the exact same moment. That the voltage is the same at every single point along a wire. That's the simple picture. And honestly, for most everyday circuits, it works perfectly fine.
Now, this whole idea has a formal name. It's called the lumped parameter model. It works by lumping all the messy, real-world physics into these neat, ideal little components. But it only works because of one critical assumption, the fine print, if you will. The physical circuit has to be much smaller than the wavelength of the signal running through it. And that fine print, that's where everything starts to get really interesting.
All right, so there's our rule, our golden rule. The circuit size has to be way, way smaller than the signal's wavelength. This isn't just a friendly suggestion, it's a core law of physics that decides when our simple model works and when it completely shatters.
Just take a look at the difference here. On the left, that's our comfy, lumped world. Signals seem instantaneous, and you can use simple rules, like Kirchhoff's laws, to figure everything out pretty easily. But on the right, that's the distributed reality. Here, the circuit is big enough that the signal doesn't just appear, it actually travels as a wave. You can't use the simple rules anymore. You have to break out the big guns, the full, powerful Maxwell's equations, which are the fundamental laws of all electromagnetism. And the thing that flips the switch, that pushes us from one world into the other, it all comes down to frequency.
So, think about it. We're always pushing our technology to be faster and faster, right? We're cranking up the frequency. And that has a direct, unavoidable consequence.
Yep, shorter wavelength. It's a fundamental relationship in physics. The higher the frequency, the shorter the wavelength. Suddenly, a circuit that seemed tiny to a long, lazy, low-frequency wave looks absolutely gigantic to a short, frantic, high-frequency one. The rule that held our whole simple model together is now completely broken.
And this quote just nails it. The simple model isn't wrong, exactly. It's just a special case, a shortcut, really, that we use to make the math easier. The real world, the more complete and complex reality, is always distributed.
Okay, so this isn't just some abstract physics lesson. Where does this model actually break down in the real world? Well, let's start with something you're probably using at this very moment, a computer chip.
Just think about it. The processor in your phone or computer operates at gigahertz. We're talking billions of cycles every single second. At those insane speeds, the signal's wavelength shrinks down to the microscopic level. Suddenly, those tiny copper wires connecting all the transistors, they're called interconnects, are actually huge compared to that tiny wavelength. They stop acting like simple pipes for electricity and start acting more like tiny chaotic antennas, with signals bouncing around and interfering with each other. And this is the critical part. Engineers can't use the simple model anymore. They need incredibly powerful software that solves the full Maxwell's equations, basically creating a perfect simulation of the electromagnetic waves inside the chip, just to make sure the darn thing even works.
All right, so let's take a huge leap. We're going to jump from the microscopic world of a computer chip all the way out to the cosmos, because we're going to apply this exact same rule to an experiment searching for the most mysterious stuff in our universe, dark matter.
See, a lot of scientists think dark matter might be made of this hypothetical particle called the axion. So they've built these incredibly sensitive detectors, which are basically cosmic radios, tuned to listen for the incredibly faint signal an axion might give off.
And this right here, this is one of those detectors. Now, here's the cool part. This whole experiment is designed on purpose to be a lumped element circuit. The whole idea is to look for low-mass axions, which would create a signal with a very, very long wavelength, much larger than the meter-sized detector itself. Sound familiar? It should.
Right, so in the world of physics, they have a ridiculously long name for this, the magneto-quasi-static approximation, or MQS for short. But don't let that fancy term fool you. It is the exact same convenient lie we talked about from the beginning. It's all built on the same assumption, that the wavelength is huge, so the signal is simple and you can model the entire detector with basic electronics.
Okay, but here's the million-dollar question.
What happens if the axion is heavier than we thought? What happens when we try to tune our cosmic radio to a higher frequency to go and find it?
Because a heavier axion means a higher frequency signal. And a higher frequency signal means, you guessed it, a shorter wavelength. You can see exactly where this is heading, right? At what point does our detector stop being small and start being big relative to that signal?
And this is where the research just gets wild. The simple MQS model doesn't just fail when the wavelength gets as small as the detector. No, it breaks down at frequencies 100 times lower than anyone would have guessed.
This table really shows you just how bad the failure is. It's a total collapse. The simple model predicts this supersensitive detector with a quality factor, or Q factor, of 1,000,000. Now you can think of Q factor like how clearly you can tune in a radio station. A high Q is a crystal clear signal. But in reality, the moment you cross that frequency line, the Q factor just plummets. The signal turns to noise and the detector sensitivity completely evaporates.
So, what's actually going on here? Well, the detector basically stops being a good listener and starts being a loud talker. It begins to act like an antenna, literally broadcasting that precious faint axion signal away into space. This is called radiation loss, and it just completely kills the experiment's sensitivity. The whole device starts ringing with its own weird vibrations and becomes totally unpredictable.
Okay, let's pull all these threads together. We've seen the exact same story play out in two totally different worlds. I mean, this is it. This is the universal principle right here in action. A microchip smaller than a grain of sand. A dark matter detector the size of a person. One is for your computer, the other is for exploring the universe. And yet, they are both handcuffed by the exact same rule and suffer from the exact same problem. When the frequency gets high enough, the wavelength shrinks, and the simple models we all rely on completely fall apart.
It really makes you think, doesn't it? These convenient lies, these simple models, they're everywhere in science. They're how we make progress. But as we keep pushing the boundaries of technology and knowledge, we're always going to find their breaking points. So the real question is, what other simple truths that we take for granted are just waiting for us to push them too far and discover the deeper, stranger reality hiding just underneath?